bop boom. Flip flop hop bop, weedy my boom. Boppity doppity romper room. Hey diddle 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 dum diddy doo. You be a doobie. Ding dong hop bop, hey daddy loo. Tip tap titter pat, ratty cat too. Rooty toot himble loosey loo. Boppity doppity romper room. Romper room and friends.
Okay, so today on the bench we have a Cobra 138 XLR. This is not actually the subject of the video. This one is mine. I've got piles of these things. I even have another customer's radio here. But I had done one of these. It recapped at alignment, and it was a bone stock radio, which is what the customer asked for. He wanted a stock radio. Even the clarifier is still locked in it. And sent it to him, and he can't stand it. He's just completely unhappy with the transmit audio on it. It sucks. And sent it back, and I don't know what to say. It is exactly the same as this radio. It's exactly the same as other radios I've pulled. It's the same as base stations that have the same UPD 858 chassis. It's just, that's the audio of these radios. So I want to show that, what it looks like. You know, we'll do some tests here to show what the audio looks like in the RF spectrum and the audio spectrum. So we'll look at it on an oscilloscope, look at it on a spectrum analyzer, and then we can also listen to it on a monitor radio. What I'm going to do is sweep an audio frequency from, what the heck do I have the generator set to up there? From 100 hertz, actually we'll just show you up here. So I have the signal generator set to sweep, where is my pointer? From 100 hertz to end frequency 5,000 hertz, and it'll do that every 5 seconds. So every 5 seconds it's going to sweep through from 100 hertz to 5,000 hertz. I don't want to say these have a unique sound. Pretty much every radio has its own unique sound. You know, every chassis style. Because every different chassis that's ever been made uses different type circuits. So they're going to sound different. These have a unique sound. A lot of people like them. I like the Cobra 138s. And something I've discovered is, especially with the microphones, I think that's where the big difference is. Where he's having a problem is, the microphones that I use, I think sound good on this radio, where because he sent me a microphone too. A Palomar, what is this? SL41. It may be fantastic for him, and that's why people, when they ask me for a recommendation on a microphone, I never give it. I very rarely will ever give recommendations on microphones. That's one of those things, if you're really into audio quality, that can make or break whether you like a mic or the radio, a combination, because your voice is different than my voice. And yeah, my voice over this microphone absolutely sucks. My voice over this microphone, this is a Astatic 575, sounds great. Which is, this is what I use. But yeah, I tried this microphone out, and oh my god, I mean, these radios are bassy to start with, which is one reason a lot of people like them. They really, and even that bass, there is distortion in it, but the distortion's not that bad to the human ear, because the distortion components, and I can show that, I'll take it out of sweep mode so you can look at it in the RF spectrum and see where the harmonics are. But at the low end, from about 900 hertz down, you'll see a noticeable second harmonic in the audio frequency. And if you work with sound, actually harmonics can be a good thing. And matter of fact, it's one thing that can be pushed when you're doing sound recordings, vocals and whatnot. Sometimes harmonics sound good. In this case, with this microphone, yeah, it's definitely not good. this mic, I don't know what it is about this microphone. He said he loves these microphones. And I haven't tried this on any other radios, but I can pretty much say without a doubt, I would never use one of these on a stock Cobra 138 XLR. So, like I say, this one is mine. This one is unmodified. It hasn't had anything done to it either. It's original electrolytic capacitors. It hasn't had anything done to it. It's not been restored yet, other than just cleaned it off a little bit years ago and stuck it on a shelf with the pile with the rest of them. So enough talking. Let's fire it up. So it's turned on, channel 20. We have the mic gain turned up the whole way, so up to the stop. I'm going to, when I flip it into transmit, and this line here is attached, if you look up, goes to the signal generator up there, and then the output goes through a bird directional coupler, the sample port off of that, and then that goes to a dummy load. The directional couplered sample comes off and then goes to a splitter combiner, and then that feeds the spectrum analyzer and the oscilloscope. Evenly, it's a 3 dB splitter, splits that off into both of those instruments, so we can view both of them at the same time. And then we're going to be listening to the audio on a Yaesu FT3000, or FTDX3000 is what we're going to be listening to the audio on. So let me, matter of fact, reach over here. Well, just radio's on, flip it into transmit, and I'll turn the volume up over here. Of course, this cable's about half in the way, isn't it? Yeah, it's better. And it just fell back down in. Stay. But you'll notice there is distortion. You'll see how the waveform is slightly distorted at the low frequencies. It levels out, stays at a good modulation level, and then eventually it just, it goes away. The modulation goes away. So that is, actually, I even breadboarded that just to show it. Let me turn the volume down. I just turn off the monitor radio, actually. Just turn the Yaesu off over there. Just to show you, so that where you see it, all of a sudden the modulation goes away. That starts to happen in all of these radios. Around 2700, you'll start to see attenuation. That is the low-pass filter in the audio circuit. So that's basically what I've breadboarded right here. Exact same component levels as you would find inside of this radio, or pretty much any of the Unit and UPD858 chassis. So it's a CL-CL filter circuit. So what that means is capacitor, inductor, capacitor, inductor, capacitor, basically. But yeah, it's actually comprised of 5 poly-dip capacitors and 2 inductors in series. So, you know, you'd have audio input here and audio output here. And I breadboarded this because I've never had to modify one of the audio circuits in one of these before. Most people are happy with it, and with whatever microphones people are using. Like I say, this customer, it just happens that the microphones he's using may work great on all the other radios he has, but on these radios, yeah, it sounded horrible. It was just so muffled and distorted. It was, yeah, I understand what he's talking about, why he wasn't happy with it. So I like breadboarding stuff like this. You know, you can run, do all the math in the world. You can run it through SimSmith, LT Spice simulators, which I usually will do. But a lot of times you still need to play around with a lot of the values, so it's always, anytime you're doing stuff like that, it's always good to breadboard stuff like that and do it in real life. Inject a signal, monitor the output, see what effect changing component values actually has on it in the real world. Because like I say, a lot of times simulation can only take you so far. Besides that, when you're breadboarding stuff, you don't have to worry about any distortion components, anything else that might be happening inside of the radio. You can inject a pure, very clean signal and see what the output is. So if you suspect maybe there's a circuit in the radio that's causing the distortion, you can duplicate that on a breadboard and see if it creates that distortion outside of the radio. If it doesn't, well then it's probably not that circuit causing distortion, or it is. You know, that's an easy way to figure out. But like I say, I like breadboarding stuff like this. It's very simple. Just slap a couple parts on a piece of proto board, you know, breadboard, hook it up to a signal generator, and monitor the output with a scope. But I think I've got his set to a level now where it should work just fine. So let's take a look at this again. Swing the camera out of the way so I'm not bumping into it. Get it off to the side here a little bit. And what I want to do is I'm going to take it out of sweep mode. Okay, and so I've taken it out of sweep mode, and now we just have the signal generator turned on. I want to start off at 100 hertz. Okay, so I'm going to flip it into transmit, and I'll be able to just, I mean, I can do it in any increment I want, but I'm going to do it in 100 hertz increments so you can see it won't be sweeping through. It'll be just a continuous modulation at those frequencies. So there's transmit at 100 hertz, and you can see modulation. Of course, it's really spread out because it's a really low frequency, but yeah, there's really not a lot of the low frequency getting out. And actually, let's turn the monitor radio back on so you can actually hear it. So you can hear that. Okay, and then I'll increase the frequency, so there's 100, 200. Now, one of the first things you're going to see is that looks horrible. Yes, it does. That is just these radios. That's how they are. 300, 400, 500, 600. Now, and if you look down at the spectrum analyzer, that peak right there, the lower and the upper sidebands, those are not what am I putting in right now? 600 hertz. That is not the 600 hertz tone. That is the second harmonic. The 600 hertz tone is actually right here. That's the little small bumps you see right beside the carrier. Those are the fundamental frequencies. That's the second harmonic at 1200 hertz audio. But that's what I say, kind of gives these things their unique sound, is that little bit of distortion you'll get at the bottom end. And you'll see once you get to, I think it's around 900 hertz, that distortion will disappear. You'll have perfectly clean modulation out to about 2700 hertz, and then you'll see the filter network kick in, and it'll start to attenuate the signal, and the modulation will just quickly drop away to nothing. So 700, 800, 900, and you can see right there it's still ever just so slightly distorted, and then by the time you get to 1000, very clean, no distortion whatsoever. And then 11, 12, 13, we'll just go ahead the whole way up to, so there's 27, and you're going to see that's 28. You can see how the bar has increased in size in the middle. You'll also notice how the entire waveform package has shrunk a little bit. So there's 27, 28, and if you watch down on the spectrum analyzer, you will notice both of those sidebands, the upper and lower sidebands, they're going to quickly drop off. And that's that low-pass filter network that I had on the breadboard. That's what's causing that attenuation, because that's what its job is, to prevent you from splattering into the adjacent channels. It cuts off the frequency, rate starts to attenuate it right here, and by the time you get out to your 5000 hertz channel band edges, there's really nothing left. So continue up, 29, there's 3, 3100, 32, 33, 34, 35, 6, 7, 8, 9, and there's 4000, and you can see at 4000 hertz there's absolutely nothing left. Now honestly, you don't need audio above 4000 hertz. That's such a high-pitched squeal, it's almost useless, but that's what a stock radio looks like. You turn my monitor radio back off, and then we'll just turn the sweep generator back on really quick, and we can look at that again. So that's what it looks like, a stock radio. I'll turn that off. Now what I'm going to do is disconnect my radio, and I'm going to get, what is it, the Love Machine? I don't even remember. No, it's the Love Gun. You'll appreciate this. so here is a customer's radio that was sent in. Same exact radio, Cobra 138 XLR. I have opened this up and it is 100% unmodified. Modulation limiter circuits all intact, blah, 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 blah. And yes, this is the Love Gun. And no, I did not stick that sticker on there. I do like Kiss. Not a huge fan, but I listened to Kiss in my younger years. Okay, and we'll do the same thing. We'll stick that one on here, and we'll go into transmit. Make sure I'm on channel 20. Yes, so I'm just to verify. You know, on channel 20 again. Again, microphone gain turned up the whole way. And we'll flip it into transmit. And you can see, looks exactly the same. It has the distortion at the low frequencies up to about 900 hertz, and it gets less and less the higher in frequency it goes. And like I say, by the time you get to 1000 hertz, it's gone. And then once you get to about 2700 hertz, the low pass filter kicks in and starts to attenuate that signal down till there's just no modulation left. It gets out to here, and then whoop, it just hits the knee of what's known as the knee of the filter, because it's a really sharp bend, and drops off. So, and there's another unmodified radio. So exactly the same. And before I modified the customer's radio, that is exactly what his looked like. Or the other customers, I should say. The radio in question. So, let me grab his now. So his, right here, has the covers off of it, because I've been working on it. Had to do some drastic changes in I modified not only the low-pass filter circuit, but I think a lot of his problem was with this microphone. Like I say, this just apparently, at least from just me talking into it, is a real bassy mic. And by this radio having that low-end distortion to start with, it just exemplified it and made it sound even worse. Where normally that little bit of distortion, like when I'm using a microphone like this, it actually sounds good. Those second harmonics at the low frequencies actually aren't bad. With that mic, it just, yeah, it wasn't good. So, radio's on. The antenna, yeah, everything's hooked up. So again, well, you can't see it for the tape. We're on channel 20. Again, mic gain turned up the whole way. Now this one, what I've done is actually, well, there's several modifications, but the main modifications were done in that low-pass filter, and what was causing that low-end distortion, these they're early, you have to remember. These radios were made before, like, the boards used in the Cobra 148s. They had a rather neat, unique, I'm not sure what word to use, but the microphone amplifier circuit had a separate mic AGC circuit, so automatic gain control. Normally you see an AGC circuit in your receiver. That's why you prevent front-end overloading. It senses big signal coming in, and it can turn the gain down of one or more stages in the front end of the radio to prevent, distorted audio. That's basically the same simulated, they've basically done the same thing in the microphone amplifier circuit. That's the microphone amplifier in these is a integrated circuit, and it's a two-stage low-noise amplifier package. And then the mic AGC circuit samples the output of that amplifier, and then can, through a pair of switching transistors and a demodulation diode, actually it's the demodulation diode, you have a positive voltage on either side, and as the cathode side becomes more conductive, eventually that'll forward BIOS the diode turns on and can then start to turn on a pair of transistors. But what that does is the second transistor is tied to the microphone input, right at the input of that mic amp, and it will ground that signal. It'll start to filter off some of that signal to ground. And that I think that was mainly what was causing that low-end distortion. That circuit, it doesn't work very well at low frequencies. So I've had to modify that to prevent that horrible, well, at least in the case, especially when using this mic, what was causing horrible distortion in the low frequencies. So radio's hooked up, we'll key the mic. And you can see we no longer have that distortion at the low audio frequencies. And you'll also notice that at the we have continued modulation at a higher level out farther for, at higher frequencies. So you can watch, all these cables, can't get my hand in here. So as you watch that come across, you can see it gets out to about just almost 4,000 hertz. And that's where you're probably about 4,000 hertz, you're probably at about the 3 dB down point. And then it tapers off really good. If I stop it and do some marker and delta measurements, which I actually did, by the time you get out to your 5,000 kilohertz band edge, I think it was like, well, here, actually, let's just do that. So I'll stop the sweep generator. Whoa, not 7,000 hertz. Switch over to the hundreds position. So we'll get right to there. And let's take a delta measurement. No, actually turn that off. Normal. Peak. Marker. Delta. No, and maybe watch the little number there. That's going to scroll across the screen over here. I'll put that on the peak right there. Okay, and we have 16.2 dB down. So it varies. If I go out to 5 kilohertz, it'll actually be, if I turn the modulation up to 5,000. And it's like 16.8, but it's really starting to drop off there. So, and then I'll spin back. So there's 4,000 hertz, and you can see where before at 4,000 hertz we really had hardly any modulation. You can see it's still holding pretty good. Before, where it was really starting to attenuate at like 2,700 hertz, here we're at 3,000 hertz, and you can still, we have good modulation. I'm just increasing the frequency, so I'd say right about there. That's where the knee is on this filter. So now the filter doesn't really start to kick in until about 3,400 hertz, and then it starts to attenuate. But even then, it's such a sharp knee. It's a little bit more gradual taper on that filter. And then actually, if I increase the bandwidth on this, on the spectrum analyzer to, let's say, 20 kilohertz instead of 10, we can actually view it as it gets out into the adjacent channel. So that's 5,000 hertz. So that would be the edges of channel 20 where we're at, and then this over here, you'd be one channel above and one channel below. And you can see that's where it really starts to drop off. But like I say, you're already at like 16 to 17 dB down by that point. Go back to 10 kilohertz. But the main thing is you get down into, which I think was his problem, was that low end distortion. As we go down in frequency, so we'll get down to, there's 1,000 hertz right there. There's 800, 7, 6, 5, 4, 3, 2, 1. Yeah, it's not, you're not going to hear anything. And if we turn the receiving radio on over here, so you can actually hear what's being transmitted. So there's 200 hertz, 300, 400, 5, 6, 7, 8, 9, and 1,000. So turn this poor radio off before we get the RF section in this thing too hot. But I think that ought to cure his problem. Like I say, it was just, he's not used to these. He's used to using apparently modern radios, like specifically the Lincoln 2s. He's used to the audio characteristics of a radio like that. This ain't that radio. This is a much older, by several decades older radio. And yeah, I think it was just the combination of microphone, in addition to his voice, what he's expecting out of it, and yeah, that mic, this radio, and him was not a good combination. A factory stock radio. Like I say, most people, I personally like these radios unmodified, but Yeah, with some tweaking, and actually the filter network in this I went from that, which would be actually what, a 1, 2, 3 pole filter. I went down to a 2-pole Butterworth style filter. So that's actually what this has in it now. I've basically removed 1 pole, changed all the values, but I've gone from a 3-pole filter down to a 2-pole Butterworth style filter on the for the low pass filter. And like I say, that increased the top end a little bit, but it's still, by the time you get to your channel edge, you're down about 16 to 17 dB, so that's considerably down. And then once you start to get into the adjacent channels, yeah, it's just whoop, it just plummets after that. So there you go. There's some of the stuff I have to deal with. Not everybody's always happy with stuff. You will occasionally get a radio back, especially when you get somebody that gets a radio like this. That and I don't know exactly what they were expecting. I guess they were expecting the audio frequency response out of the Lincoln 2. And like I say, these radios aren't going to do that. Turn it off. Yeah, I think now he'll be happy with this guy. I've actually added some adjustments inside the radio now. Like I said, I had to completely redo that mic AGC circuit, so now actually that's adjustable, where before the mic AG, and actually let me just show you on the schematic. So there's the mic AGC, so there's your microphone amplifier, your microphone jack, comes into the microphone amplifier. Like I say, that's a 2-stage integrated circuit they're using for a microphone amp. A sample of that comes out, goes to the mic, and this is the mic AGC circuit down here. And like I say, you can see all that does is once that final transistor, once that starts to conduct, the transistor starts to turn on. All that's doing is bleeding off that audio to ground, is all that does. And then that audio then comes across, goes through your mic gain control. Your AMC circuit comes in, is tapped in. You have another mic amp, and then you have this right here was the original filter network that was the low pass filter network that really had that sharp need that really started to kick in around 2700 hertz. So like I say, modifying that filter to increase the top end frequency range, but still having good attenuation, so you're not splattering into adjacent channels. So that's the problem. A lot of times what you'll see is people just bypass this filter. That's a bad idea. Completely removing this filter, this entire filter system here, is not a good idea. You're guaranteed to splatter into adjacent channels, and besides that, unless you're a bat, you're not going to be hearing those extremely high frequencies anyhow. So we want to have good attenuation, but yeah, I think he'll be happier with that. Now the radio has, honestly, well, actually the Lincoln 2 Plus that he's using, actually, because those radios honestly have a fairly narrow audio frequency response too. I had done a modification in that radio, but that's what he's used to using. This radio now has a very similar curve to what that radio that he's currently using is kind of using as an example, or to compare the radios. So I think he'll be a lot happier with this now. But yeah, he wanted stock. That's what he got, was stock. So now it's not stock.